So let's walk through the physiology of circulation and go through some of these terms. So the first term, and this is a term we'll use a lot, is blood flow. Blood flow is exactly what it sounds like. It is the volume of blood flowing through a vessel, through an organ, or even we can talk about blood flow through the entire circulation at a given period. We always measure blood flow as mils per minute. If we are talking about blood flow through the entire circulation, we call that cardiac output. Okay, and we've seen that term before. So cardiac output is the amount of blood that you put out through the entire circulation in 1 minute. And remember, when we talked about cardiac output, I told you that it is essentially 5 liters. So you move your entire blood volume every minute through your body. Okay, that's your cardiac output. Now, your cardiac output is very consistent when you are at rest and your heart is contracting at normal sinus rhythm of about 75 beats per minute. But it can vary a lot through individual organs. So again, it just depends. Did you eat? We're going to be sending more blood to your GI tract. Are you working out? Well, you're going to be sending more blood to your muscles. Another term that you should be familiar with is this term blood pressure. Blood pressure is the force that blood exerts on a vessel wall. So again, I always relate this back to a water balloon. Think of a water balloon. If you were to take a water balloon and just fill it up with a little bit of water, well, then there's not much pressure in there, right? But if you fill it up really big, ooh, it's getting so big this might explode, there's a lot more pressure in there. So it is the force that the blood in your vessels is exerting on the vessel wall. And it's this pressure gradient that is the driving force for moving blood through your body. So again, remember the drawing, okay? We have blood leaving the left side, the left ventricle at 120, getting into your capillary beds around 35, leaving your capillary beds around, leaving your capillary bed around 17 or 14, and coming back to the right side of the heart around 0. So that pressure gradient is really helping to drive blood through your arteries, capillary beds, and veins, okay? From high pressure to low pressure. And then one of the last terms I want to walk you through is this term resistance. Okay, resistance. When I think of that word, I think of Star Wars and I think of the resistance. My brother was a huge Star Wars fan when I was growing up. And the resistance is just opposing what's happening, right? So resistance is opposition to flow. It's making it harder for the blood to move. It's basically the friction that blood is encountering as it's moving through a vessel. There are 3 things that will contribute to the resistance of blood movement. One is blood viscosity, how thick your blood is, okay? I want you to think about a straw in a cup, okay? Now let's think about different fluids that you could suck through that straw. Let's say it's water. It's pretty easy to suck water up through a straw, right? Mm-hmm. Now let's take a fluid that's really thick, syrup or honey. You put your straw in that. How hard is it to get that up through the straw? It's hard, right? So resistance is going to be influenced by blood viscosity. How thick is your blood? Remember, the more red blood cells you have, the thicker your blood is. Now, in reality, your blood viscosity does not change much. In reality, you are not changing your hematocrit all the time. Now, if you go to a high elevation, yeah, you'll make more red blood cells. Your hematocrit will go up. But otherwise, your hematocrit for ladies, we're about 45%, okay? So that's pretty constant. The other thing that will really influence resistance to flow, blood vessel length. Okay? Remember, as your blood moves through a vessel, it's going to encounter friction. So the more vessel it's got to move through, the more friction it's going to encounter. Okay? Now, we are also probably at an adult stage, we're done growing. So we're not constantly building more longer vessels. We're about where we are, okay? We're just maintaining at this point. So we're not really making our blood vessels much longer. So as an adult, this is also pretty constant. And then lastly is vessel diameter. I want you to think about a blood vessel, okay, and think about the friction it's going to encounter if the vessel's nice and big, or if it's teeny tiny and constricted. Okay, which one would have more friction? A big vessel or a restricted vessel? Yeah, one that's small, one that has gone through vasoconstriction. So blood vessel diameter is going to play a big role on resistance. And in fact, this plays the greatest influence on resistance because this is constantly changing. You are constantly changing the size of your vessels depending on where you need to send blood. The other two, blood viscosity, vessel length, you're not changing that much. Those are pretty constant. Even though they play a role in resistance, the one that is constantly changing is vessel diameter.
Is that the vasoconstriction and vasodilation?
Yep, vasoconstriction and vasodilation. And that's constantly changing. You eat a meal, it's going to change. You exercise, it's going to change, just based on your body's demands. So let's put all of those together. Let's talk about flow, pressure, and resistance. So we say that blood flow is directly proportional to pressure, okay? Directly proportional means it goes in the same direction, okay? That's what directly proportional means. If blood flow goes up, then blood pressure goes up. If blood flow goes down, blood pressure goes down. Directly proportional, okay? Blood flow is inversely proportional to resistance. Okay? If resistance goes up, flow will go down. Inversely proportional means they go in the opposite direction. So if there's more resistance, then blood's not going to flow as well. It's going to go down. If there's less resistance, blood's going to flow great. It's going to go up. Okay, so those are inversely proportional. So here's the equation. Okay, we say that blood flow is equal to a change in pressure over resistance. Resistance is more important in influencing flow because it's easily changed by vessel diameter. Bless you. We are not typically changing our blood pressure, are we? Blood pressure is 120/80. What we change mostly is resistance, vessel diameter. So that's going to have a greater impact on blood flow than your pressure is, because we're not changing our pressure very